Hi, welcome to your MECH 200 Statics online classes. In this video, we continue through the topics of Chapter 4, in which we are going to study the different aspects of force system resultants. I hope you enjoyed this class. A very interesting concept often used in mechanics is the principle of moments. In simple terms, it states that the moment of a force about a point is equal to the sum of the moments of the components of the force about the point. To illustrate this principle, let's suppose that we have a 3D force system in which two forces F1 and F2 are acting to cause a rotation about point O. We can calculate the resultant moment by simply taking the resultant of the two forces and calculate the cross product with the position vector r. Since the resultant force is the vector sum of the two forces, and as we saw before, the cross product obeys the distributive law, we can simply calculate the moment as the sum of the moments caused by forces F1 and F2 individually, without the necessity of calculating the resultant force first. For 2D problems, the application of the principle of moments gets even more appealing, since instead of using the moment arm D and the resultant force F to calculate the moment using this equation, we take the rectangular components of the force Fx and Fy and the coordinates of the point of application of the force x and y and use this scalar equation to calculate the moment. Now, let's work on one example. In example 4.5, we are asked to determine the moment of the force about the point O for the bar shown here in this figure. We have different ways to solve this problem, depending on how we want to play with the information given in the problem statement. One way to solve this problem is through the calculation of the moment arm D from trigonometry. From the problem data, we can easily get it from the sine of the 75 degrees angle multiplied by the length of the bar, which results to 2.898 meters. Then, we can calculate the moment by simply multiplying the given magnitude of the force by the moment arm D and find the answer of 14.5 kilonewtons meters clockwise, which according to the right-hand rule makes the moment directed into the page. The second way we can solve this problem is through the application of the principle of moments, in which we have to take the x and y components of the force and the x and y coordinates of the point of application of the force. Then we have to apply the scalar notation of the principle of moments shown in slide number 2. It's important to note that both components of the force act to create a moment rotating clockwise. Thus we have the negative signs in this equation. Since all important angles are given the problem statement, we just need to apply some simple trigonometric relations to determine the force components and the coordinates x and y of the point of application of the force. Then we substitute all values into the moment equation and get the same final answer. A third solution for this problem is possible if we place the x and y axis parallel and perpendicular to the rod's axis as shown in the figure here. In this case, the component of the force projected in the x-axis doesn't cause any moment about the point O, since its line of action passes through this point. Therefore, we just take the y component of the force, Fy, and multiply it by the length of the rod to get the moment. By taking the sine of 30 plus 45 degrees, which is 75 degrees, and multiplying it by the force magnitude, we end up having the same negative 14.5 kilonewtons meter we've got in the other two solutions. Now you're ready to study example 4.6 of the textbook on your own. Before you do that, Make sure that you fully understand both the scalar and vector applications of the principle of moments presented in slide number 2. Now, we're going to learn how to calculate the moment generated by a force about a specified axis. Let's take, for example, this common situation in which we need to get the lug nut of a car tire loosened. It's easy to understand here that because of the L shape of the wrench, the force F applied at one of its ends will create a moment that tends to rotate the wrench and the nut about the point O along both X and Y axes. However, the nut can rotate only about the Y direction. And then the component of the moment in the Y direction is the moment of interest for this case. And we don't need to care about the moment component in the X direction. To determine this component of interest, we can use either a scalar or vector analysis. Let's start with the scalar analysis. To use this method, first we need to determine the moment arm, or perpendicular distance from the axis to the line of action of the force. In this case, the length of the wrench in the y-axis, or dy. We calculate this quantity by taking the cosine of the inclination angle theta of the distance d, and apply the scalar formulation of the moment to get its magnitude. According to the right-hand rule, mi is directed along the positive y axis, as shown in the figure. In general, we can use this scalar formulation to calculate the moment about any specified axis A. Now, let's see how to solve the same problem using the vector analysis. The first thing we need to do is to determine the position vector for the moment arm to calculate the moment. Then, we apply the vector formulation of the moment, and having both the position vector and the force vector written in the Cartesian form, we apply the determinant equation to get the Cartesian representation of the moment. Next, we take only the component of the moment in the y direction and consider it as the vector representation of the moment of interest. Finally, for any specified axis A, we can find the moment in this direction using the dot product between its unit vector UA and the moment caused by the force, represented by the cross product between the position vector and the force vector. When we expand this equation, using the Cartesian notation for the unit vector and the determinant notation for the cross product, we end up having this final vector equation that allows us to calculate the moment about any specified axis represented by its unit vector UA. Now let's work on one more example. In example 4.7, we have to determine the resultant moment about point O caused by three forces, F1, F2, and F3, respectively applied to points A, B, and C of the figure shown here. To solve this problem, we have to identify first the moments generated by each force along each one of the axes. To do so, we have to recognize that a force is parallel to a coordinate axis or has a line of action that passes through the axis, like the force F1, which is parallel to the y-axis, does not produce any moment or tendency for turning about that axis. Then we have to define the positive direction of the moment according to the right-hand rule, as shown in the figure, in which the positive direction of the moment points towards the thumb of the right hand. Therefore, to calculate the component of the moment only in the x direction, we have to consider the force F1 in its moment arm of 2 feet formed by the height of the box, which causes a rotation towards the positive direction. The force F2 and its moment arm of 2 feet formed by the half of the box length, which also causes a rotation towards the positive direction. And for the force F3, the moment is 0, and the final answer for the moment component in the x direction is 220 pound-foot. For the component in the y direction, we have that F1 does not create any rotation effect about this axis. F2 and its moment arm of 3 feet, formed by the width of the box, cause a rotation towards the negative direction. And F3 and its moment arm of 2 feet, defined by the height of the box, also causes a rotation towards the negative direction of that axis. And the final answer for the moment component in the y direction is negative 230 pound-foot. For the moment component in the z direction, we have that F1 does not cause any rotation effect because it's aligned with this axis. And F2 has its line of action crossing the z-axis, which makes the resulting moment caused by this force about the z-axis equal to 0 as well. Then, F3 and its moment arm of 2 feet, defined by half length of the box, is the only force that causes a negative moment about the z-axis, which results to minus 80 pounds-foot. And finally, once we have all the three components of the moment, we calculate the magnitude of its resultant by taking the square root of the sum of the squares of the moment components, and the final result is 328 pounds-foot. It's your time now to go through examples 4.8 and 4.9 of the textbook on your own. Before you do that, make sure you fully understand both the scalar and the vector analysis applied to the calculation of the moment components presented in slides 8, 9, and 10. And with that, we are done with the third part of chapter 4. Thanks for watching, and I'll see you in the next video.